Hey everyone. So here we're working on a problem where we have a more complicated circuit. Not very complicated, but a little bit more complicated than we've dealt with. So let's suppose here we have a 12-volt battery and then we're given the values of each of the resistors here. So I've gone here and labeled this one R1, R2, R3, R4 just because I've made this chart here just to keep track of what I know and what I don't know. So since I know my battery provides 12 volts, the potential difference across the battery then has to be 12 volts since energy is conserved. And I don't really know anything about current at this moment, but I do know all these resistances. And then I kind of circled this spot here because the number right there is actually my total resistance. Because that way I can solve for what the current running through the battery is, which is going to help us. Right? I also wrote down here what I needed to solve for. You want to find current and the change in voltage for each resistor. And I have also written here Ohm's law. So we know Ohm's law is true, at least assuming we're dealing with ohmic resistors. And the other thing I'll use are Kirchhoff's laws, both his loop law and his, what was it called? The loop law and junction law, there we go. Right, so loop law says that around any loop, the change in voltage should be 0 since energy is conserved. And the junction law says that at any node, right, so these here are examples of some nodes, the total current going into that node is equal to total current going out of that node. And that's because of conservation of charge. All right, so looking here, let's find the total voltage. Now to do that, we need to find the equivalent resistance for this circuit. So if I were to replace all of these circuits here with one circuit, all of these resistors here with one resistor, and what would that be? So doing this here, it looks like it's going to be easiest first to simplify these two resistors here, which are in parallel with each other. All right, we know when resistors are in parallel, that's going to be equal to 1 over the total resistance in parallel here is going to be the sum of 1 over all of those resistances. Okay. So looking here, so 1 over this, I'm going to write this as REQ for these two guys here. That's going to be 1 over 400 ohms plus 1 over 600 ohms. So here, let me use my calculator since I did not crunch these numbers earlier. So you got 1 over 400 plus 1 over 600, and we take the inverse of that answer. And we get 240. All right, so the resistance here is 240. So I'm going to redraw my circuit to kind of show that simplification we've made. All right, so now we've got our battery. We still have R1 going on here. But now we've got one resistor here, which is now, 240 ohms. Actually, instead of R, I'm going to write the exact value since here we're just simplifying. And this is 560 ohm. Well, now this is better here. Well, let's see. So when resistors are in series, that means we have the same current running through them. So kind of looking here, we have one wire, and it doesn't split off anywhere. So these two resistors here are in series. All right, so let's just add those together. So we know when resistors are in series, they simply sum. All right, so since we have 2 here, we just add those numbers together. So we have 240, and we add it to 560, and we get 800. So we have a equivalent resistance here of 800 ohms. So redrawing again. Oh man, sorry, my battery kind of got jumbled up there. Got our 800 ohm resistor here, and now those two resistors have an equivalent resistance of also 800 ohms. All right, so now we see here all we're left with is 2 in parallel with 800. So I'm going to take 1 over 800, add it to 1 over 800, and take the inverse of that answer, and we get 400. So our equivalent resistance here, so if we were to take all these resistors and make it one resistor, we just need 400 ohms. Okay, so that makes it simple. So now we can actually calculate the current running through this battery, right? And since this is the positive terminal of our battery and we're dealing with conventional current, that's going to be flowing upwards. So the current at that location, well, we know V equals I times R. So to solve for current, we take the voltage and divide by our resistance. So that's going to be 0.03. So that's 0.03 amps. So not very much current going through. So that means going into this junction, we have 0.03 amps. All right, I'm not going to draw that here. All right, so we know that here we have a node, so the current's going to split. So part of that 0.03 is going to go down to this resistor, and the other one's going to feed the rest of this circuit here. Looking at the circuit here, what jumps out to me, now let's apply Kirchhoff's loop law, because I see here we have a very simple loop with one resistor, which is very nice. All right, so doing that, that's going to help us because we know that the voltage going around here has to drop to 0. Starts at 12, has to end up at 0 if we complete the whole loop, right? Another way of thinking about it is we have, if we start at this point, going upwards, we gain 12 volts, right? So then we have to lose 12 volts to get back to our having a change of voltage of being 0. So doing that here, we know that we have 12 volts all in that one resistor, so we can actually label that here. That has a voltage drop of 12 volts. So therefore the current is going to be 12 over 800, giving us 0.015 amps. Well, that's very nice. So downwards here of 0.015, well, that's just half of 0.03. Right, so that means we know coming out of this junction here has to also be 0.15 amps. Hopefully we can all see this. All right, so now we know entering this node here, we have 0.015 amps, and it's going to split into the upper and the lower. They're not going to split evenly, all right, and we can see that because they have different resistances here. Now, actually, looking here, like, oh, that's interesting. It's split evenly here in this case, even though I have a whole bunch of resistors. That's because basically what we're looking at is this bottom case we did here. All right, entering in, we have 0.03 amps. Then we have 0.15 going down to the 800 ohms. That means this equivalent resistance, so the resistance of all these added together, is also 800 ohms. So it has to have the same current being split. So that's why same current being through that part of the circuit. So that's why that is. All right, what could be useful here? Well, looking here at again, we're dealing with the junction law. Once the current splits, it has to come back together. And once it comes back together, the total number of charges didn't change per unit time. So coming out of this circuit, or out of this junction, excuse me, has to be 0.015 amps again. So that means running through resistor 4, we know our current is 0.015 amps. All right, so then we can actually calculate the voltage drop in resistor 4. All right, so we just take our 0.015 amps, multiply it by 560 ohms, and we get 8.4 volts. All right, so we have a voltage drop of 8.4 volts there. Now, let's apply the loop law again. So starting from this corner here, we know we have to have, let's say, 0 volts because we're coming back to the battery. So we gain 12 volts here, so we don't have to lose 12 volts overall. All right, so let's take, I take the most, I don't want to say direct path, but the most straight line path in the way I've drawn this circuit. So I know I have some sort of voltage drop here and some sort of voltage drop here, and I return. Well, from that 12 volts, we know 8.4 is deposited there. So to my 400 ohm resistor, it's just going to be 12 minus our 8.4, giving us 3.6 ohms in resistor 3. By ohms, I mean volts. So we have a change in voltage of 3.6 volts through this resistor. We can do the same logic here with the upward path, and see that we also have 3.6 volts up top. And now we can just very simply take the voltage, divide by the resistance to get our current. So we have 3.6 divided by 600, giving us 0.806. And then also 3.6 divided by 400, giving us 0.009. Just to check, I'm going to add those two together to make sure. sorry, that's not 806. I misread my calculator. 0.006. Add those two together. We get 0.015, which is what we expect with our junction law. All right, so we can apply Kirchhoff's laws here to basically solve more complicated circuit diagrams.